Please go ahead.
Okay, get this. All right. Okay. Thanks, Hauta. And first, I would like to thank the organizers for giving me this opportunity to speak in this exciting conference. This is the first in-person conference I attend since a few years ago. So this is literally exciting for me. And I'm looking forward to many discussions. So today I'm going to talk about anomalies in lattice systems. And this is work in collaboration with Nadi Seiberg. All right, so, oops, sorry, let me make a move. So I think most people would agree that anomaly, especially tooth anomaly, is one of the intersection areas that's most fruitful between condensed matter theory and high-energy theory in the past decade or so. Okay. So first, I'll start with a quick review of what tooth anomaly means. The way that I phrase it will be more close to the way that field theorists would like to phrase it, but same idea applies to lattice systems. Okay. So first, I'll review the formulation in Euclidean quantum field theory.
I think the slides is not updated.
Somehow I didn't share. Wait. Maybe I should just restart sharing. Sorry, this is annoying. I'll do it again. Hopefully this one's going to work. Let me make sure that it's updating. No? Okay. I think it's probably because I'm clicking instead of. Sorry for this. Hopefully.
Just don't share. Just
try one more thing. I'll just share the desktop. Maybe this will do a better job.
Yes, that works.
Okay. All right. Sorry about this. So now it's updating. Okay, so first let me review the formulation of tooth anomaly in Euclidean quantum field theory. So let's imagine we have some quantum field theory with a zero form and invertible because we are generalized symmetry is not out of room in this conference. So just say that it's a zero form symmetry, internal symmetry, G. And whenever the theory has a symmetry, we can couple the theory to a background gauge field. And let me just call it A. Okay. And we can study how the theory transforms under a gauge transformation. So let's say A is transformed into A of lambda, where lambda parameterizes the gauge transformations. So it's all very schematic here. And the partition function of the theory could transform by a phase vector. Now, if these extra phases cannot be removed by redefinition of local stuff, local counter terms, then we say there's a tooth anomaly. Okay. So I'll not say much about anomaly inflow in this talk. I'll just treat tooth anomaly as a property of the theory itself. Okay, so when we have tooth anomaly, well, one of the reasons that we care about tooth anomaly is that we can do tooth anomaly matching, because this calculation is really independent of the scale. So we should get the same result from the UV, the ultraviolet, and the IR series. And that puts some constraint on the dynamics. Once we know the anomaly from the UV, we can say something about the IR series. Okay. And this will be preserved under the RG flow. So this is the more like field theorist view on the tooth anomaly. And now, as a condensed matter theorist, I guess every condensed matter theorist probably bound with lattice models. We're more used to lattice models. So let me also give a quick review of what we mean by lattice models and what we expect to learn there. Okay. Sorry. So here by lattice models, I mean, for example, like a spin chain. So it's a discrete system. Okay? And the Hilbert space of this system is a tensor product of finite dimensional Hilbert spaces. They can live on sites, on links, on spaces. Okay. And we also allow to put local constraints. So Hilbert space is not necessarily a tensor product. Also, all the examples that I will discuss will be tensor product Hilbert spaces. Okay. Now, in this system, we usually have Hamiltonians with geometrically local interactions. So roughly, we can think of lattice model as a discretization of the continuum space, although there are more features than just that. So it's a local lattice model. And we usually have translation symmetries, at least for the purpose of this talk, I'll assume translation symmetries so that there will be a well-defined infinite system limit. An important example that will come back again and again later is the spin 1/2 Heisenberg chain. Okay. This is a model with long history, and we're still learning new things from this model. So in this model, it's a one-dimensional chain, and on each site we have a spin 1/2 degree of freedom. So the spin operators are denoted by S here, and the J labels different sites. They are labeled by integers. And I'll always work with finite-size system. So the sum goes from 1 to L. So there are L sites in the system. And the interaction that I write down here is a nearest neighbor Heisenberg interaction to just Sj dot Sj plus 1. We can add more terms. Okay, but let's focus on these two terms, on this term. Now there's this hypothesis that's we love and we use it all the time, is that lattice systems, most lattice systems, if not all, should have a nice continuum field theory description, at least if we only focus on the low energy physics. Okay. For example, in this example of a spin 1/2 Heisenberg chain, the continuum limit, the continuum theory of the Heisenberg chain is SU2 level 1, Wessel-Miller-Witten conformal field theory. So all the low energy physics should be captured by this conformal field theory. And one of the goals of this talk is to really make this very precise. To extent, we can capture the low energy physics, all the symmetries. Okay. All right, so now let's also discuss symmetries in lattice models. Again, in the lattice model, we can also have zero form global symmetries. Okay, and I won't have higher form or non-invertible symmetries in talk. You just know old-fashioned zero form global symmetry. Okay. In lattice model, we also have lattice symmetries. Okay, so which will be called G of lattice, and they consist of discrete translations, discrete rotations, or parity symmetries, etc. So that's the space group of the lattice. Now, the fourth symmetry group of the lattice model is just putting these two things together, the internal symmetry and lattice symmetries. Oftentimes, it's just a product of these two groups, but doesn't have to be. So generally, we can write the lattice symmetry as a quotient of the fourth symmetry by the internal symmetries. And I'll use GUV to denote the symmetry of the lattice model, the fourth symmetry of lattice model. Now, let's compare this with what we expect from a continuum theory. So what often happens is that the continuum theory has more symmetries than lattice model. So that will be denoted by G of IR. Okay. And of course, this G of IR contains certain zero form symmetries and maybe more. And importantly, the IR theory usually has, well, almost by definition, has continuous translation because it's a continuous field theory. And often it has the continuous rotation. And we often deal with Lorentz invariant series. Then you really have the whole Poincare space-time symmetry group. Okay, so we have a symmetry group of lattice model. And we also have a symmetry group of the continuum theory. And they should be matched somehow. What that means is that there should be a homomorphism between the UV symmetry group and the IR symmetry group. Okay. So this homomorphism describes what's often called the symmetry enriched theory in literature. This is how symmetry, the lattice symmetries or the UV symmetries sort of interplay with IR symmetries. I want to say, please interrupt me with any questions. Now, the question that I like to think about is that how the lattice model goes to the continuum. So, what's the journey to the continuum? Okay. A lot of times, it's just a very smooth and safe shape. There's no subtleties. You just directly take the limit of L goes to infinity, and you get a continuum. So let me just give one example of a very smooth limit. No surprises. So that's another prototypical lattice models that we encounter often in condensed matter systems or in condensed matter physics, this quantum Ising model. And this is again one-dimensional chain where each side has some spin 1/2 or qubits. There's no SO3 symmetry. And there are two terms. There's the Ising interaction and the transverse field. The details do not really matter. Now let's look at the UV symmetry of this model. So the internal symmetry is only the Z2. We can flip all the spins and then the model remains the same. And you also have lattice symmetry. So let's say you have L sides. It's a translation invariant model. So you have the ZL translation symmetry because there are only L sides. And I forgot to mention that all these one-dimensional systems I'll be talking about have periodic boundary conditions. So L translations is the same as identity. So the ZL group. And you can also have parity on lattice. Okay? So that's all the symmetries you have on lattice. Okay, so what's a continuum theory? Well, at least near the critical point, we know that this model has a critical point. Near the critical point, we can describe this model by a relativistic real scalar phi-to force theory. In 1D, the critical point would be Ising CFT. You can deform the CFT to reach the other faces. In general, it's a real scalar phi-to force. And the symmetries of the continuum theory will have, again, the Z2 symmetry that just takes phi to minus phi. But now the space-time symmetries is enlarged to a Poincare symmetry. And the mapping between the UV and IR is very straightforward. The spin flip symmetry, the phi is the order parameter sigma z, basically. And this spin flip symmetry just phi goes to minus phi. It's literally the same Z2. And the translation becomes almost just an exponentiated version of the continuum translation. So we say that the low energy spectrum of this system on finite size has a very smooth L goes to infinity limit. For example, at the critical point, forgot to put that in, at the critical point, the spectrum would just be described by the spectrum of CFT, where we can write down the formula, exact formulas for the low energy spectrum, just following the finite size scaling of the CFT. Okay. There's nothing surprising here. This is what I mean by a smooth limit. However, sometimes the limit is not so smooth. So that happens a lot in these spin 1/2 systems where we have more symmetries on the lattice. For example, the antiferromagnetic Heisenberg chain that I mentioned earlier, and also, for example, Z2 spin liquid in 2 dimensions, etc. There is still well-defined quantum field theory in continuum. But as we'll see, taking the limit of L goes to infinity is trickier here. Okay? And just to give kind of one-sentence summary of what happens, the different limits, there are different limits depending on how we take the L goes to infinity. The different limits correspond to quantum field theory's invertible defects inserted, which I'll say a lot more about this later.
Excuse me, I have a question. Is this Ising model with antiferromagnetic coupling? It also have similar non-smooth limit, I imagine.
Yes, so it has non-smooth limit, also fits here, right? Although it's less subtle than, for example, the Heisenberg chain, because there's no anomalies.
Okay.
Right, that's another example. Yeah, thanks. I just want to quickly mention this, just to put it in the same context, that we also know there are even more severe violations, well, more severe, like non-smooth limit, and these happen in the fractal models, where we know that there's very strong mixing between the UV and IR. So lots of information of the UV lattice model leaking to the IR. Okay, and we see that in sub-extensive symmetries and ground state degeneracies in almost all of fractal models. And this is just a, I'm not sure that the next sentence really means anything, but it almost feels like different sizes related to inserting non-invertible defects. I'll just put it there. Okay, so I won't talk about fractal models. I'll just talk about these milder non-smooth limits. For example, in the Heisenberg chain. Okay, so to kind of see visibly what happens, let's look at the finite size spectrum of a Heisenberg chain. Okay, so I should have written down Hamiltonian, just the nearest neighbor Heisenberg interaction. And here I plot the energy levels and eigenstates labeled by SZ and lattice quantum numbers. So this is K, the logarithm of the eigenvalue of translation, lattice translation. Okay. And here are two plots, one for 16 sites, one for 18 sites. There are lots of details that are hard to keep track of. The points are on top of each other. But first, you see there's a linear dispersion. One can clearly see, even on this finite size. So that says that it's a CFT-like spectrum. Now, the red circled dots, these are the actual ground states on the finite size system. And what we see that the ground states shift their lattice quantum number, the momentum, depending on whether this is L is a multiple of 4 or it's 2 mod 4. When L is multiple 4, the ground state's at 0 momentum. When it's 2 mod 4, it's at momentum pi. Okay, so that's some interesting feature that we like to understand. We can also put the system on a chain with odd size. Okay, and here I only plot from 0 to pi. And you see that now the ground states are close to pi over 2. But again, there's this mod 4 dependence on whether it's to left of pi over 2 or it's just right to the pi over 2. Okay. So from this finite size spectra, what we can see is that the continuum limit seems to strongly depend on L mod 4. Okay. There's obvious L mod 2 dependence because if L is an even number, you have even number of spin 1/2. That's you can find a singlet. If L is odd, then it's always at least 2-fold degenerate, but the actual periodicity is 4, not 2. Okay, so this is something that I like to understand from the point of view of field theory, continuum field theory. Sure.
Why is this a problem with the continuum? I mean, those 2 points.
Well, that's exactly the question. No.
You think you can repeat the question?
Yes. Okay, let me repeat the question. So the question is, why is that a problem in continuum? Because it seems like you can fuse the 2 points together. Is that right?
Yeah.
Yeah. Yes, that's why it's a question, because on lattice we see that the dependence is mod 4, but naively we would think that in continuum we shouldn't have a mod 4 dependence. And the answer to that is that because there's some anomaly associated with the translation symmetry, which I'll make precise. Okay, yeah, thanks for the question. Okay, so now another thing related lattice phenomenon, we can say that is a Lieb-Schultz-Mattis theorem. Okay. So this is a theorem that was discovered by Lieb-Schultz-Mattis in 1961. Actually, they proved it in appendix of a paper. So let's again think about a translation invariant spin 1/2 chain with spin rotation symmetric interactions, like a Heisenberg chain. And you can solve this model exactly for the nearest neighbor interaction, but in general, if you have more interactions, then it's not solvable. But what Lieb-Schultz-Mattis proved in the appendix of the paper is that on the chain of length L, again with periodic boundary conditions, the gap to the first excited state has to scale as 1/L. Okay. Now, if we paraphrase it, it means that you cannot have a unique gapped ground state. And that strongly constrains the possible dynamics of these models. You can either have a gapped system, like a CFT, or we can spontaneously break translation. In 1D, we cannot spontaneously break SO3. So, Okay, so this theorem is a non-perturbative exact statement about possibly strongly interacting lattice models. So it's not easy to have such statements, and they have been generalized in many directions in recent years to higher dimensions, finite internal symmetries or point group symmetries, and there's also a rich connection to crystalline SPT phase and all that. Okay. And what has been sort of appreciated is that this Lieb-Schultz-Mattis theorem should really be understood as a mixed anomaly between the translation and the internal symmetry, in this case, SO3 here. Okay. All right. Now, if we want to say it's anomaly, then we should be able to do anomaly matching with, with the symmetries. Okay. And this is how it's done, at least the popular way that this is done in literature, is that we simply pretend the translation was an internal symmetry. Okay. And oftentimes, if we take an infinite system, it's just Z. Now we formally introduce Z-valued gauge fields for translation. Here I call it X. X is formally the gauge field of translation. And we can write this 2+1 action. Also, I said I don't want to talk about an inflow. In this case, this is 2+1 action for the anomaly. And it's written in terms of the gauge field of translation X, the cut product with the Stevie-Winnie class of SO3 background gauge field. Okay. And let's not ask what it means to have a gauge field translation formally. This is believed to give the right physics. Now, what happens in the continuum theory is that usually we have translation takes this form. So obviously it's going to contain the continuous translation. A is the lattice spacing, so e to the I momentum times A, just translating by that amount. And on top of that, there could be some discrete symmetries coming from the internal IR symmetries. Okay, so this is what translation usually looks like in the continuum theory. Now we can match anomalies with this Z cross SO3 with anomaly of the internal IR symmetries, just like how we match anomalies for internal symmetries. Okay. Pretending that translation just the internal one. Okay. And this has been used a lot and produced expected results in all cases. Okay. And a closely related idea is that we should think of a system of finite size. Let's say we want to increase the size by 1, adding 1 more spin. How do we describe that in continuum theory? Well, if we treat this more seriously, then it means that increasing the size by 1 is equivalent to having this G of T, the internal symmetry that emerges from the translation, G of T twist, have that twist in the continuum theory, have that defect in the continuum theory. Okay, so the rest of talk, I'd like to make some of these statements more precise, have a framework where we can discuss this on a somewhat more rigorous footing. And we'd also like to test this idea. This idea of increasing L is the same as adding internal symmetry twist. How far we can take this, and to understand the spectrum of this finite size system. Okay, so so far it's more or less like a review of the known results, and now I'd like to discuss how we think about all of these phenomena. Okay. All right. First, since we want to discuss two anomaly, we have to think about defects or background gauge fields. Okay. So it's standard to construct defects of internal symmetries. We can do it in continuum or we can do it in lattice. There's no problem either way. And since we are thinking about a 1+1D system, and we don't want to impose relativistic symmetry from the very beginning, we have a lattice model. There's no relativistic symmetry to begin with. We are limited to this particular space-time manifold. where we have a space is a circle. I mean, it's really a lattice, but we can think of it as a circle times imaginary time, let's say. Okay. And we can think about background gauge fields on this torus, on this two-dimensional torus. So there are essentially these two. This is the most general configuration of gauge fields we can imagine. The vertical direction is time. So we can have a G twist in the spatial direction, or we can have an H operator inserted in the time direction. We can think of it as a twist in time direction. And they have to commute, that's all. But let's be a little more careful. So let's say the spatial circle is twisted by some internal symmetry G. Okay? So G is an element of the internal symmetry on lattice. Now, when we have a twist in the spatial direction, the symmetry of the lattice model is modified because of that twist. For one thing, only these symmetries that commute with G survive when we add a G twist. So we have this G of G. So when I write the parentheses and put a G, it means that things that happen when we add a twist, G twist in spatial direction. And I'll use this notation very often. So this is more or less like the centralizer of G in the G internal symmetry, and including the translation and all that. Okay. And we can discuss a twisted partition function, which is a e to the beta Hamiltonian evaluated in this twisted sector, but we are also allowed to insert H in the time direction, just an operator inserted into the trace. Again, this H has its H of G because this symmetry could be modified in the presence of a G twist. Okay. So we can roughly say the time circle is twisted by this H from the group, symmetry group in the presence of G defect. So here, we are assuming that G is internal because we only know how to do internal symmetry twist. However, H may be internal or a lattice symmetry. This setup was, I believe, used before, for example, in Oshikawa's classic paper on Lattinger theorem. Okay. So let me make a few remarks. First of all, as I already mentioned, H of G may differ from H of 1, at least when we look close to the G defect. And I should also mention that imagine a G defect to be a very localized one at some point in space. Sometimes you can spread it out continuously, like when the defect is U1, but just to be uniform, I'll assume that G defect is localized at some point. Okay. Secondly, the group relations may also be modified compared to the untwisted sector. And lastly, but also importantly, this symmetry G of G may be represented projectively, and that's related to anomaly. So just to give an example of a modification of group relation, we can think about what happens to a translation symmetry. So the symmetry defect is supposed to be a topological defect, so you can move it around. And if we do a translation, you move the defect. So the naive translation is no longer a good symmetry in the presence of a defect. So you have to combine this with a shifting of the defect back to where it was. Therefore, we call it T of G, which is T, the naive translation, just move everything to the next side, followed by an operator that moves the G defect back. And now the group relation is modified without a G defect because we have L sides, T to the L is 1. Now with a defect, when we move it, we drag the defects around. So T to the L is now applying the symmetry to the whole system. And you can see pictorially from this picture that if we just drag this defect, a G defect going vertically, we drag it around, we're left with a horizontal line which represents an operator inserted into the theory. So this is a relation that we'll use a lot. Okay. All right, so now let me consider an example of a two anomaly on lattice, two anomaly of internal symmetry, but in a lattice model. Okay. Of course, there has been many discussions on how to formulate this, and here we'll discuss a way to look at it. In this framework that I just introduced on torus, we have defects, and we look at how symmetries are modified in the presence of defects. Okay. How much time do I have? I have.
Half an hour.
Okay, all right. It's more than I thought. Okay, so I can probably slow down a bit. Let's consider a spin chain. Again, no, this is all about spin chains. And the symmetries I'll discuss is U1 cross Z2. So no, for no good reason, let's just consider symmetry, U1 and Z2. And the spin chain, there are a couple of different ways to formulate this spin chain, but I'll choose this way that seems to be the most convenient. We'll think of it as a lattice gauge theory, 1 plus 1D. Okay. So we have some spin 1/2 sitting on the dots, and we have Z2 gauge fields sitting on the crosses, the red crosses on the link. Okay. So Hilbert space of system is a spin 1/2 chain, the tau spins, coupled to a gauge field, Z2 gauge field mu spins. Okay. So to make it gauge theory means that we have to impose Gauss law. No. So here the charge of the Z2 is a tau Z. So tau Z has to be equal to the gradient of the electric field, which is the product of this mu x on the two links connected to the site. Okay, so that's a standard Z2 gauge theory on the in the one-dimensional system. So this is our system. If you don't like gauge theory, we can reformulate it without any gauge constraint by essentially doing a Kramer-Warnier transformation on this system. But turns out that for discussion of symmetry is more transparent in this formulation.
Sorry. The U1 symmetry is the in-plane rotation of tau.
Yes. So I just showed it on the screen. This is the U1 symmetry.
Oh, okay. Sorry.
Yeah. So here the U1 is generated essentially U1 is essentially just the rotation on tau. But because now a part of U1 is already gauged, right? So tau Z is already the gauge symmetry. So to get a phase for global symmetry, we put a quarter coefficient in front. Okay, so the charge of this U1 is the sum of tau Z, but with a quarter coefficient in front. Okay, yes.
Does tau Z squared something like that?
Yeah, tau Z squared identity. Tau and mu Z satisfy the standard Pauli algebra. Tau is tau Z, tau x, y, z, the Pauli operators. The square root. Oh yeah, okay, yeah. Let me repeat the question. So the question is whether tau squared to 1 and why this is a U1 symmetry. So that's the next line. Okay, but let me first discuss the Z2 symmetry and then I'll come back to the question. Yeah. So the Z2 symmetry here is just measuring the holonomy of a Z2 gauge field. So it's a product of the mu z's, the connections. Now, in order to claim that this is a U1 symmetry, I need to show that this Q is an integer charge. Okay, Q is an integer, quantized to integers, then we can say that it's a U1 symmetry. So let's assume L is a multiple of 4 for this discussion. Okay. Then just doing a little algebra, we can see that e to 2 pi q is actually equal to 1 with a Gauss law, with the help of a Gauss law. So Q has to be quantized to integers, and you can check that it actually takes all integer values, well, up to some upper bound set by the lattice size. Okay. So this is a lattice system. And in a way, it's actually a simple one because we start from a spin chain of tau with a U1 symmetry, and we gauge a Z2. And when we gauge Z2, as I'm sure many of you know, that when we gauge Z2 symmetry in 1 plus 1D, you actually get a new Z2 symmetry, which is the X here. And these two symmetries have a mixed anomaly. So how do we see that on lattice? Well, let's follow the general kind of procedure and just try to insert all kinds of defects. First, let's try to insert the X defect. So remember, the X is generated by the Wilson loop of the Z2 gauge field. So we can put an X twist, which just means that we modify the Gauss law at some point, at some site. Okay, so let's pick some site N and just say the Gauss law picks up an addition minus sign, almost like having a Z2 charge sitting there. This is the X twist or X defect. Now, because of this modification to a Gauss law, this relation e to 2 pi q equals 1 when we derived it, we actually used the Gauss law. Naively, you get a product of tau z's, and then we can use Gauss law to rewrite it, and you get 1. But now there's an extra -1. So what it means is that e to 2 pi iq is actually equal to -1, not 1. So now the charges, U1 charge is quantized to half integers. So in the presence of X defect, the U1 charge takes half integer values. And that's that's a standard kind of manifestation of this mixed anomaly between U1 and Z2. We can also insert a U1 symmetry defect. So let's say I insert the e to the I sigma q. Sigma is now just some angle between 0 and 2 pi. So inserting this twist means that we modify the link variables. We don't write down any Hamiltonian, so it might be a little abstract. But if you imagine any sort of Hamiltonian, then this twist means that we modify, for example, the link variables in some way by some phase. Now, because of this 1/4 coefficient, we can roughly say that these tau spins now carry half charge under Q. So if we ramp up this sigma from 0 to 2 pi, inserting a 2 pi twist, that actually modifies the link variables mu of z some point by a minus sign. So what that means is if we track how the system evolves as we increase sigma from 0 to 2 pi, the eigenvalue of the Wilson loop has to flip sign. Okay? This is commonly referred to as the flux insertion in many condensed matter literature. So as we insert 2 pi flux, we change the Z2 eigenvalue. So these are sort of the manifestations of a mixed anomaly in this lattice model. There are other ways to see it, but no, this is close. This is within this kind of formalism that we are using. Okay. All right. So now I'd like to move on to the Lieb-Schultz-Mattis theorem and discuss how to do it with the translation symmetry. Okay. Again, the setup is the same. We have a space-time torus. A space is the lattice. Time is continuous. We can insert internal symmetry defects in the spatial direction, any of them. And we can insert any symmetry defect as long as it commute with the spatial twist. Then we can put it in a time direction. Now, in this context, the spin-1 half chain, the Heisberg chain, for example, the symmetry, internal symmetry of the lattice model is just SO3. Okay. Now, the lattice symmetry will be ZL. So let's ignore the parity symmetry for now and just say, we consider a translation. So the internal symmetry defect you can insert up to conjugation is just a rotation around SZ, let's say by sigma. And because of the SO3 group, we have the identification. Sigma is supposed to be a 2 pi periodic variable, and it's the same as sigma minus sigma because of the X rotation. Now, in the presence of such a defect in the spatial direction with the twist, the symmetry group is, in this case, just reduced. The internal symmetry group is reduced. So when sigma is 0, there's no twist. We have the full SO3 symmetry. That's fine. When we have a generic value of sigma different from 0 and pi, we only have a U1 rotation remaining because of e to I sigma as z. We can only now rotate around the z direction. Okay. Now, if you have a special value sigma equals pi, then the symmetry is enhanced a little bit. On top of the U1 rotation, we also get a Z2 that takes sigma to minus sigma but now sigma is pi, so sigma minus sigma is the same. So we get additional Z2 that forms O2. So we can now play this game, putting all of this in a time direction and also maybe put a translation operator in a time direction. Okay. And we can think about, for example, this twisted partition function, where we have a sigma twist in a spatial direction, but we can insert, for example, t to the nth power. T of sigma is the translation in the presence of the sigma defect. Okay. And we can also put e to the I psi sz in a time direction. Okay. And we can check various relations that these partition function satisfies. as a function of sigma n and c. So for example, we get these two relations just from operator identities. They are all really just consequences of operator identities in the lattice model, but now phrased as relations of partition function on the parameters. For example, if we increase n by L, increases n by L, because of relation T to L equals I sigma S Z, it means that we have to shift C by sigma. So this is one relation. Now, the setup still has this, the setup, if we apply the X rotation to the setup, you can flip the value of sigma and C. So that's a second relation. So these are relations satisfied strictly without any phase. So that's something you can derive. Now, the following two are more interesting. If you look at the expression of T of sigma, the translation in the presence of a defect, the additional operator you have to put in to make it the actual translation is a spin rotation on one side. Remember, on one side, we have spin 1/2. So now if we shift sigma by 2 pi, we'll pick up a minus sign, depending on how many translations we insert in time direction, because it's a spin 1/2. So that's a -1 to the n in the third relation. The last one is just a simple fact that if you have all number of spin 1/2, doing a 2 pi rotation will produce a -1. So if you shift the C by 2 pi, you get a -1 to the L. Now, if you look at these two relations, they're actually somewhat space-time symmetric. If you switch n to L and then swap C and sigma, these two relations map to each other. So it's kind of saying that we can really think of L and N on equal footing. Okay. All right, so these are one way to see that there's this something going on the lattice, the Lieb-Schultz-Mattis kind of anomaly from the additional phases that pop up in these relations of partition function. Okay. Now, let me give another way to see that something anomalous is going on by looking at a different set of defects. Okay. So on the previous slide, I only insert really SZ rotation symmetry defects in space and time, and also translation. But when sigma equals pi, we have more symmetries, so we allow to put in more defects in the time direction. So what I'm going to consider here is that let's put in the pi rotation of SZ along the spatial direction and put in the pi rotation along X in time direction. They commute. The pi rotations always commute in SO3, so we can do this. So this setup essentially only requires a Z2 cross Z2 subgroup. The pi rotations consist of pi rotations of the SO3. So really just a Z2 cross Z2 symmetry. Again, we have a spatial circle twisted by the pi rotation around Z, and we are putting the pi rotation around X in the time direction. But now, because the translation again picks up this additional e to the I pi SZ on one side, now the translation anti-commute with e to the I pi Sx we insert in the time direction. Okay. So what it means is that when we put in a pi Sz defect, now the Hilbert space transforms projectively under the translation, the twisted translation, and the pi rotation of X. So you get the projective representation of the remaining symmetry group, which involves the translation. That also leads to the exact statement of a partition function that when we put in sigma equals pi and c equals pi, the partition function has to vanish if n plus L is odd integer. This argument was also given in this last reference by Yale and Oshikawa. All right, so these are ways to see the anomaly on the Lieb-Schultz-Mattis anomaly on lattice, phrased in a manner that can be used to do anomaly matching. Because the same statement should hold in the continuum theory. Okay, so let's now come back and look at, just to remind you of the spectrum of Heisenberg chain again. Okay? So the Lieb-Schultz-Mattis anomaly matching has been discussed, as I said, has been discussed a lot in literature. So what we are adding here is a slightly more systematic way of formulating it. But no, so the Anomaly matching has been done many times. Now, in the remaining, the focus will really be on understanding the finite size spectrum of this Heisenberg chain from the continuum theory. Okay. So these are just some plots of the spectrum that I showed earlier. But the key thing that there's this mod 4 dependence of the lattice quantum numbers of ground state. Okay. So first, let's discuss how the symmetries of lattice model are mapped into the continuum theory. So unfortunately, I messed up things a bit. I'm using some of the notations that I'll define on next slide, but I'll come back to this later. Okay. All right, so the two questions we want to address, I mean, really one question, how do we understand this range spectrum from continuum theory? We know that continuum theory is SU to level 1. Can we derive the quantum numbers and especially lattice quantum numbers of this finite size spectrum from the knowledge of continuum? All right, so to do this, I need to spend a few slides on the continuum theory. It's SU to level 1 CFT, but all the discussion so far really only involves the O2 subgroup of SO3. So we can think of the continuum theory just as a compact free boson with a radius equals 1 in some convention, R equals 1. Okay. So this is just the same as SU to level 1 CFT, because we don't need the SU2 symmetry, so this is good enough. Just to make sure that we're talking about the same thing, here are the Lagrangians. For field series, maybe you like this, the relativistic Lagrangian more. The radius is R, the first one. And in condensed matter literature, you probably see the second one more. No, this is in terms of two variables, two dual variables, phi and theta. But if you integrate out theta, you get the first one. And that will also give the relation between the parameters k and r. So k is just r squared in this case. The symmetries of this model is the following. So you have two U1 symmetries. One of them just shifting phi, the other one shifting theta. It's more transparent in the phi theta Lagrangian. So you have two U1 symmetries. So one of them is called the momentum symmetry. This is a string theory terminology. So obviously I just borrowed it. And the other one is called winding. Okay. And then there's a Z2 symmetry that flips phi to minus phi, which will also flip the momentum winding charge. So Q of M and W are the charges of the two U1 symmetries. So that's all the symmetries we get for a generic value of R. For spectral value of R, like R equals 1, you get more symmetries, but no, this is good enough for our purpose. Okay, so let's discuss twists in this free boson CFT. Again, we'll only consider twists by the U1 elements, the U1 cross U1 elements. So we can consider twists by this G of the two twist parameters. A of M is the angle of the U1 rotation, U1 momentum rotation. A of W is a winding, U1 charge, U1 winding rotation. So we can consider a general twist like this one. And we can study how the system, the spectrum changes, the quantum number changes as we insert a twist. For example, the momentum charge will be modified by this amount. So this is additional eta W, the winding phase, divided by 2 pi. And similarly, there's a change in the winding charge. The continuum momentum will also be modified when we insert this twist. The first two relations are basically the mixed anomaly between the two U1 symmetries. Cool. So this is called the spectral flow. States and quantum numbers change continuously as we put in these twists. And we can check how they change with the parameters. Now recall that we have this important relation on lattice that T to the L is equal to G. G is a symmetry that we twist the spatial direction. So we can try to do it in this free boson CFT. Okay. And T to L, in that case, is just a full rotation of the spatial circle. So we can do a full rotation e to 2 pi I times the momentum and see what we get. Okay? We'd like this full rotation to be equal to the spatial twist, the symmetry element that now twists the space. However, see that we can only do it with a slightly unusual form. So remember, G is U1 rotation in the momentum and U1 rotation in the winding. So this momentum is the momentum charge of the U1 CFT, not the actual lattice momentum. You see that the momentum charge is the one that twisted by 8 of W, so the one that in the presence of twist. But in order to satisfy the relation without additional phase vectors, because that's what we have on lattice, we have to modify the winding one to be the one without the twist. Okay? So naively, one would expect this to be the e to the I q of m in the presence of twist, and e to the I eta w qw in the presence of twist. It turns out that to get rid of all the extra phases, we need to modify the winding charge or the momentum. But no, this is the convention. We choose to modify the winding charge so that we don't have any extra phases. So the punchline here is that the winding charge in the twisted sector is represented by the expected winding charge in the presence of twist, but the momentum. But winding charge is the one that without a twist in order to satisfy this T to the L equals G relation. Okay, so as an example that will be important, let's consider this particular symmetry element, the group element C, which is pi rotation in both momentum and in winding. And this will be related to translation in the spin chain. Okay. And let's consider a twist by C to the nth power, and also a momentum, U1 momentum twist by sigma, which is equal to this choice of the twist parameters. And now we can just compute the representation of this C transformation in the twisted Hilbert space, and this is what we get. We get I to the n times e to the I pi. Now the qm0 plus qw0, these are integers. So we already see something resembling the mod 4 dependence, that this C has this funny phase vector I to the n in front of it. With this choice, the relation for rotation equals the symmetry defect is satisfied strictly without a phase. All right, so far everything's in continuum. So now let's connect this back to the Heisenberg chain. Okay. So unfortunately, I have to go back a few slides because it's only written there. So now I've introduced all the notations, but first let's quickly remind ourselves how the symmetries act in the continuum. On lattice, we have SZ conservation. The SZ charge is identified with a momentum charge in a continuum theory. There's also a pi rotation around the x-axis that's identified with a charge conjugation R symmetry in the continuum. Importantly, T acts as C times e to 2 pi I over L P. That's just a continuum translation, but there's additional element C. And we can see that at least from the spectrum of the system, when L is a multiple of 4. Okay? We can identify these symmetries clearly in that case. Okay. Now let's use this to predict completely the spectrum of low energy states, the quantum numbers. So I have to advance a few slides. All right. Now to do this, we need to invoke this. You can say this is a postulate that a chain of which I've already mentioned a few times, a chain of length L, we should think of it as the continuum theory, SU to level 1, with L defects C to n twist, where n is L mod 4. Okay, but let's say C to L. That doesn't change anything. So with LC defects inserted. So that means we can now write down the twist parameters. Remember, we also put in a SZ twist by sigma, so that's the twist parameters. Now with this assumption, we can go and calculate what the lattice translation should really look like in the continuum theory in the presence of all these twists. And we get the exact formula for the lattice translation. So there's a continuous translation that's kind of we expect. And we also have this C, but now in the presence of all these twists. And the formula for C, we also derived earlier in the continuum theory. So now we have just an explicit formula for the lattice momentum for the low energy spectrum of the Heisenberg chain. Okay, so I think I'll probably skip this so we can do the anomaly matching and with these formulas and get results that we expect. So let me directly jump to this slide where we calculate the ground state momentum from the formula that we just derived from the continuum theory. Okay. So for even L, we'll get I to the L. So for even L, the ground state is in the Q equals 0, Q bar equals 0. These are the chiral charges, but no, doesn't really matter. And we get I to L. And see that there's L mod 4 dependence. For odd L, we have fourfold degenerate ground states. And we can also calculate for the ground state momentum. You see that there's this additional pi to 2L. If you still remember the lattice spectrum, this is not exactly a pi over 2, but a slightly 1 over L shift. We can also get a 1 over L shift. What's somewhat surprising is that this formula even works for L equals 2. So let's do that. This is a quantum mechanical exercise. If you have a chain of 2 sites, and with Heisenberg interaction, we all know the ground state is being singlet. Now, what's a translation? Translation just swapping the 2 sites. So that eigenvalue is -1. And L is 2 gives you -1. So it even holds for L equals 2, where we don't think of it as a Heisenberg chain. And you can check that even works for L equals 3 for all the values, essentially. All right. So, no, we can do all these calculations from continuum, but coming back to the question, why there's an L mod 4 dependence. Here, let me give a somewhat more heuristic argument of why the dependence is mod 4, not mod 2. Okay. What happens if we just fuse the 2 sites together? Again, we're going to use this sort of postulate that a chain of length L is a continuum theory with L C twists. Just replace N with L C twists inserted. Okay. Now, we know that a C symmetry actually has anomaly. The C has a Z2 Topf anomaly. And one way to describe the anomaly, this is what I learned from Schuhan's paper, is that you can think of it in terms of crossing relations between the C defects. So if you want to have, so on the left and right here, there are 2 configurations of C defects which look the same outside this small region, but inside this small patch, we reconnect the C defects. And this reconnection will produce a minus sign. This is a signature of the anomaly. Okay. Now, let's think about the following calculation. Okay. Let's imagine we have 2 C defects in the spatial direction, and we want to ask what's the eigenvalue of C in the presence of these 2 C defects. So this calculation was done, the space-time rotated version was done also in this paper that I cited, but let me do it again. So with the crossing, we need to resolve them because there's really no meaning of crossings in this 1+1 picture. So we can resolve it in this way. This is the most natural way to resolve it. That gives us some kind of defects wrapping around the torus. And now we can reconnect them using this crossing relations with the extra minus sign. And now the defects are deformed into just a straight line, an operator insertion in the time direction. So what these pictures really mean is that C is actually equal to -1 on the states with 2 C defects. And that's the interpretation of the mod 4 dependence. When you put in 2 additional C defects, well, the 2 D defects can be fused into a trivial defect, but at the price of a minus sign. And that's the minus sign we see in the lattice momentum. Therefore, this mod 4 dependence, the I to the L, is really the lattice precursor or lattice manifestation of this anomaly of the Z2 symmetry. All right, so am I running out of time already, or kind of? Okay, so yeah, 2 more slides.
Yeah.
So we can generalize this. I'll be quick here. So we can generalize this to more general systems. Let's assume that the L infinity limit depends on L mod M. M is a periodicity, okay? Which means that the eigenvalue of translation will have this additional phase factor, and they depend on L mod M. Okay. We can further assume that the C actually generates the emergent Zn symmetry, little n, which is a subgroup of Zm. Doesn't have to generate exactly Zm. The Zm doesn't have to act faithfully. We could actually just have a smaller subgroup. And with some mild assumptions, for example, the series relativistic symmetric, we can derive some relation between these quantum numbers. And so I'll skip this. So in the end, for example, in terms of the Heisenberg chain, what happens at m equals 4, mod 4 dependence, but actual symmetry is Z2. But then there is this zeta equals -1, that's a signature of anomaly. Okay. All right, and we can do it for SUN level 1 spin chain, SUN spin chain whose continuum series SUN level 1. I'll just discuss the last line. So following this analysis, we can calculate the lattice quantum numbers of the ground state, and we'll see this finite dependence on the SUN n when it's odd, and when the length of system is a multiple of n, so you get SUN singlet, then the lattice momentum does not depend on the length at all. When n is even, we see an alternating sign of lattice momentum, which again we can understand from the anomaly of the emergent Zn symmetry from translation. All right, so unfortunately, I guess I'll have to skip this last slide where we apply the same ideas to Luttinger or the filling constraints, okay, which is not true for the anomaly. So that's maybe the only thing I want to say, but really a manifestation of this relation between translation and the symmetry that we use to twist the system. But in any case, so this is a summary of the talk, and thanks for our attention.
Is there any question?
Not exactly. But when can translation symmetry is not on subset.
Yeah.
But it doesn't always get mapped to like a pure
Doesn't always. Yeah.
anomaly in the field. So
Right.
Is there any like connection you can make to say when translation is anomalous by itself?
Could you repeat the question, please?
Yeah, I'll repeat the question. The questions, so question is whether we can predict when translation maps to an anomalous symmetry in a continuum. I think that's the question. I guess the general answer is no. We don't really know a way to predict whether the translation, because essentially means that we have to know what the translation looks like in the continuum. That has to be done on a case-by-case basis. Because different systems they have different continuum limits, and we really have to work on the system and figure out how translation acts. What we can say that if you see this dependence, mod 4 dependence, some sort of funny dependence on the lattice momentum, then that probably is a sign that there's something anomalous going on with the translation. That's one lesson we learned from this exercise. And these things, of course, Heisenberg chain has been studied to this mod 4 dependence was solved from beta ansatz or from many other ways, although not from the anomalous point of view anomaly. But this is something you can check easily from, say, just exact diagonalization of Hamiltonian, and that will tell you whether you expect some anomaly or not, in the context of spin chain at least.
There's a question from
Oh, okay. Sorry, I couldn't see that, I guess.
John. Go ahead.
Could you say a little more what you mean by saying that the filling constraints are not related to Tufte anomalies?
Yes. So, okay. Yeah. So thanks. So I can talk about this slide. All right. Again, this is essentially the setup that was used in this classic paper by Ashikawa. We consider, let's say we have a 1D system with some U1 symmetry, U1 charge being Q, and we twist the spatial direction by e to the I sigma Q, and we put in translation and also U1 symmetry operator in the time direction. So we can study this torus with these twists, and everything summarizing this partition function with a t to the n and e to the I cq inserted in time direction. So we can study how this partition function transforms with this, the parameters, a relation with the parameters. And the last one is the reason that we get this fitting constraint. The last one follows from t to the L equals I e to the I sigma q. So what it means that naively we will think of a translation as a z to the L group, ZL group. So n and n plus L should be the same, but it's really not in this case because of a twist. So when we shift n by L, we have to shift c by sigma. So it's not a simple function on this parameter space. There's some additional twists. Now, there's no phase involved because anomaly is really the statement that there's relations involve additional phase factors, but here there's no phase. This is just equal. The partition function, the parameter space, what it means that the parameter space is not the one that we naively think it is, has more structures. It's like a twisted bundle or something. Now, here, I'm not fixing the charge Q, so you don't see any phase. If we fix the charge Q and look at the partition function, almost going from a grand canonical ensemble back to a canonical ensemble, then we'll see that the partition function, when we shift n by L, we'll get some additional phase. And that's, if we think about it, it's just saying that t to the L is now equal to e to the IQ sigma. So if you fix Q, t to L is a phase vector. And for an extensive system, we usually fix a fitting. So that means the lattice momentum is quantized to 2 pi over L, integer multiples of 2 pi over L plus mu times sigma. And that's the well-known statement from, say, Ashikawa. Okay. And then we can track how things change when sigma advances by 2 pi and all that.
So at fixed charge, it isn't a Tufte anomaly.
In the fixed charge, it looks like a Tufte anomaly. It's not a Tufte anomaly because we know there's no Tufte anomaly for U1 times translation of this form. U1 times Z, or if you like. But it does look like a Tufte anomaly when we have a fixed charge. And we can use it like Tufte anomaly to constrain the Lagrange dynamics. So I guess that's that's the best I can do.
Okay, thanks.
Right. And another reason that we don't like to think about the Tufte anomaly is that the filling is something can do continuously. So at least it's not one of these usually Tufte anomalies associated with a quantized anomaly inflow to the bulk. We don't have that bulk. The parameter is continuous here. So you may sometimes you see this is referred to as the unquantized anomaly because there's a continuous parameter mu you can tune.
I think we're running late in time, so
Okay.
maybe thanks Mom again. And then
Thanks.
we'll reconvene.